Alright guys, let's move on now. Let's move on into hypothesis testing. So at this point now we're entirely in the realm of inferential statistics. In the realm of inferential statistics, you're trying to find statistics that can help out to infer something about the population, to find out something about the population. So I will teach you three main types of inferential statistics, which is the one sample t-test, the independent samples t-test, and the related samples t-test. There's another one that I will not have time to go in length, but I will teach you what is the purpose of it. So for now, you want to make a mental list, and even though it's in the slides, you want to make sure that you write it down. Depends on what you're trying to do. The one sample t-test is used to compare one sample to a population. Compare one sample to a population, one sample t-test. The related or between subjects t-test is used to compare the same group of people twice. The independent samples t-test or between subjects t-test, the related samples t-test is within subjects. This one is independent samples t-test is between subjects. And the last one is the ANOVA, analysis of variance, and that's to compare three different groups of people. Now, as an introduction to that topic, I do want to talk a little bit about what is the null hypothesis testing. This is the most common method used to generate inferential data. And it's super simple. What is a hypothesis? A hypothesis is a guess that you're taking, an educated guess that you take. And the educated guess that you take should not be the main mindset, the main priority that you have in mind when you're conducting a study. Let's think about an example that is on the slides. What if meditation changes IQ scores? You're wondering if perhaps a program of meditation is going to increase the IQ level that people have. So what you do with that is compare a sample. You have an idea for what is the IQ in the population is 100. So you're going to get a group of people. You're going to get them to meditate, and then you're going to give them an IQ test. So you're trying to understand something from a sample, and based on that you're trying to generalize to the population. When you get into this, you have an idea in mind, which is meditation will affect IQ. That's your hypothesis. That is your alternative hypothesis. That is the suggestion that you have. However, you don't really go into science, you don't really go into those studies already with an idea of what is the hypothesis. You want to go in with a lot of skepticism, suggesting or thinking that you may not find results. So, no hypothesis implies that you go with the idea that you're not going to find results. Of course, you want to find results, but you go in with a lot of skepticism that you don't want to force results. You want to see if you're going to find something. No hypothesis is pretty much saying that nothing is happening. So let's think about it. The alternative hypothesis is meditation will affect IQ scores. The null hypothesis is going to look as similar to the alternative as possible. The only difference is the null should incorporate the word not. That's it. If the alternative hypothesis is meditation will affect IQ scores, then the null will be meditation will not affect IQ scores. That is a null hypothesis. When you go into the test, what you try to do is to, remember this word, reject the null hypothesis. That's what you try to do, reject the null hypothesis. If you can't reject the null hypothesis, then the word is you fail to reject. So I'm going to put it here. You either reject or you fail to reject the null hypothesis. Now, The alternative hypothesis, and this is going to be important as we transition into the one sample t-test. The alternative hypothesis, its symbol is H1, and the alternative can be directional or non-directional. Directional or non-directional can also be called one-tailed or two-tailed. So directional here is called either one-tailed or non-directional is called two-tailed. Either one-tailed or two-tailed. What this implies is that your hypothesis is given a sense of direction. So, if my hypothesis is saying that meditation is going to change IQ, I don't have a clue if change is going to be for the good or the bad. I'm just saying that it's going to be different. At that point, then I'm saying, I don't know where this is going to go, but I just know that it's going to affect. That's non-directional. The type of word that you use determines whether something is directional or non-directional. If I use a word like change, affect, I'm saying that it's different, but I'm not saying where the difference is at. So if we visualize a distribution like this, non-directional is also called two-tailed because it can go on one end, on the negative end, or on the other end, on the positive end. Maybe it's going to go up, maybe it's going to go down, but you don't know. You're just saying it's going to be different. What you see in the corners is called alpha. Alpha means chance or probability of error. You want to remember this as well. Chance of error or probability of error, if you want to publish a study, should be at about 0.05, 5% chance of making a mistake. You don't want to go above that, or you don't want to go below that. I'm sorry, you can go below that, but you don't want to go above that. Nobody's going to publish your study. Typically, the standard is at 0.05, and for class purposes, we're going to keep at 0.05. But technically, you can go below that. The lower you go, the more and more difficult it is to reject the null hypothesis. So most researchers prefer to keep at 0.05. So my chance of making a mistake are at 5%, and I'm happy with that as a researcher. If I just say that my hypothesis is suggesting that there's going to be a difference, but I don't know what the difference is at, then I'm making a two-tailed, and it's also called non-directional. If on the other hand, I'm suggesting that it's going to go up or it's going to come down, then it's going to be called a directional, and at that point, it's going to be called a one-tailed. So perhaps I'm going to say meditation improves IQ. The key word is improves. Then I'm saying IQ is going to go up. Then it's one-tailed, and it goes there. One-tailed can also be negative. So maybe, I don't know why, but I may think that meditation is going to decrease IQ. So decrease is a suggestion that it's going to go down, and at that point, it's going to be a negative. So think of the type of words that you can use. If it's on the positive end, you may say words like improve, increase. If it's going to go down, you can say reduce, decrease, you name it. Be very careful when you put up your hypothesis, because the way that you word the hypothesis is suggesting if you're going to go up, you're going to go down, or if you're just going to say that it's going to be different, but you don't know where the difference is at. Make sure that you review that. That's hypothesis testing, and now let's review specifically what is one sample t-test. Alright guys, so now let's move on into the actual one sample t-test. Again, we're full into inferential statistics. Once you know the steps of hypothesis testing, then now let's actually put it into practice and see how can you compute a one sample t-test. First thing, its use. Remember, one sample t-test is used to compare results from a sample and compare to a population. There can be instances where you want to compare two samples, and for that is a different type of t-test that we'll see next week. For now, this is used to compare one specific sample to a population. So let's think about this. In the one sample t-test, there's 5 steps that you take, which are the 5 steps of hypothesis testing. Step 1 is establishing your hypothesis. So let's go back to the example of IQ and meditation. I wonder if meditation changes IQ. So my null hypothesis is saying that nothing is happening. And I can say something like, meditation does not affect IQ. You can word this any way that you want. I'm just using my example. H1 is the alternative. So I'm saying here, meditation affects IQ. That's it. In the criteria, which is the second level, here what you want to know first is the probability of error. Most often it's a 0.05, what we accept. What is going to be accepted in the field if you want to get published. But technically speaking, you can go below that if you want. But you don't go higher than 0.05 because nobody likes your research at that point. There's too many chances of error. So if we're going to keep it at 0.05, we're going to have it here. What is the standard? Degrees of freedom is n-1, sample size minus 1. So let's say, for example, that we have a sample size of 10 people. So n-1 is going to be a degrees of freedom of 9. Cool? If you have this number, if you have this number, and if you already know if it's going to be 1 tail or 2 tail, remember here, whether you're giving it a direction or not, establishes if it's 1 tail or 2 tail. So if you give a direction, if you say that it's going to go up, or if you say it's going to go down, that's going to be 1 tail. If you're not given a direction, then it can go up or down. You don't know, you don't care. The only thing that you care is that it's different. So at that point, it's going to be a 2 tail. All right? And when you look into the different table, I uploaded another one called the t-table. The t-table is a different type of a normal distribution. It's a t-distribution, which is, again, from a mathematical standpoint, just a little bit different than the unit normal distribution. That table is the one that you would use if you're computing a t-test. Only for a t-test would you use that one. So open up the table right now that you have in your files, keep it open, and look into the t-critical. So let's play with the numbers. Let's say that we have 10 people in our sample, so we have a degrees of freedom of 9. Let's say that we have an alpha of 0.05, and let's say that it's a 2 tail. Look out in the table for the number for 0.05, 2 tail, 9 degrees of freedom. Stop right now the video and go for it. Stop it. Did you find it? 2.262. As long as you know your degrees of freedom, and as long as you know your alpha, and as long as you know if it's 1 tail or 2 tail, you're going to find a critical value. What is the point of this? This is a number that we have to beat when we do our t-test. If we beat this number, then we say that we reject the null hypothesis. Cool? This is the number that we want to beat. So, how do we compute the t-test? Well, first of all, from your sample, there's the estimated variance, which is this. This is called the estimated variance. There's a long formula on the slides, but technically speaking, you can simplify everything by just getting the sum of squares. The number that you see in the numerator on the slides is exactly the same number that you see here. That one is a different formula, but it's going to give you the same outcome. You can play with the numbers if you like. If you have the sum of squares and you divide it by n-1, you're going to get the estimated variance. Then, the estimated standard error. So the number that you get here, you're going to plug it here. Alright? What you want to do is first solve what is inside. So you're going to plug the number here. You're going to divide it by n, which is the number of the people that you have in your sample. And then you're going to take the square root of the outcome this is going to give you the estimated standard error. So this is the estimated variance. This is going to be the estimated standard error. If you look at it, it's very similar to how you get a standard deviation. The thing is that you're dividing the variance by n before you take the square root of that. The number that you get from the estimated standard error, you're going to plug it in the denominator. So lastly, if you're going to compare a sample to a population, the idea is that you already know the mean from the population. So say that we're comparing IQ. I already know that the IQ of the population, which is mu, is going to be 100. So then I'm going to generate data from a sample of mine. And from the sample that I get, say that we have a mean of 115. I'm going to compare this. X hat is going to be the mean for my sample. So it's going to be 115 from my sample minus 100 from the population, divided by the estimated standard error. And the number that I get here, what I want is for that number to be higher than the critical value. This is called T obtained. So my T obtained should be higher than my T critical. If my T obtained is higher than my T critical, then guess what? I reject the null hypothesis. And for this example, reject the null hypothesis and conclude that meditation affects IQ. If on the other hand, I get a T obtained value that is lower than T critical, then I'm gonna fail to reject the null hypothesis and conclude that meditation does not affect IQ. That's it. One thing though, one last thing. Let's say that I believe that meditation decreases IQ. Let's say that for whatever case, I decide that meditation is going to actually affect negatively IQ. So I'm already predicting that IQ is going to be lower than 100. If that's the case, it's a one-tailed, right? It's a one-tailed because it's directional, but it may be one-tailed negative. If it's a one-tailed negative, just remember, this is super important. If you get a one-tailed negative, the critical should be negative. So the same way that I find the number, the only difference is I'm going to make the number now negative. And when I compute everything here, I'm predicting sample mean that is going to be less than the population mean. So this number should be lower than this, and it should give me a negative outcome. If the outcome of the obtained is negative, I should be on the right track. But in this case, we want something that is more negative. That's the only difference. That's the only time that you want to see something more negative. So see, for example, if we have a negative 2.262 as a critical, for me to reject the null hypothesis, I want to find something like a negative 2.5. If I find that negative 2.5, then I reject the null hypothesis. This is more negative than this, then this would reject the null hypothesis. But if instead I get a negative 2, the critical is more negative than my obtained, so at this point I fail to reject the null hypothesis. Everything depends on what you're looking for. If you're looking at something that is non-directional, then don't bother, just try to get a number that is more positive. But if you want to make it the directional and you imply that it's going up, you want something that is more negative. But if you find something that is going down, it's going to be then something that is more negative. To wrap it up, I just want to tell you one thing. Say that, again, based on this example, I know that the population mean is 100 and my sample mean is 115. You may be tempted to say, well, 115 is more than 100. This already tells me that it's different. Why would I have to go through all this crap? The thing is, in a statistically valid way, just saying that your number is higher than the other is not enough. Maybe you only tested this meditation on 2 people and you got 115, and you want to say then, this is enough for me to say that I can generalize to a sample. From a statistical standpoint, it's not a fair number. you want to find something in a statistically valid way that takes into account the sample size, that takes into account the probability of mistake, and all of that is coming from those steps that you're taking. So this is now what differentiates someone that is actually trained and skilled in statistics from someone that is not. You guys learning this now can differentiate and say that you're going to be skilled in knowing how to compute a t-test. Those kind of things now make you more valuable as far as future professional. Review the class activities, review the examples, practice with the homeworks, and if at any point you get stuck on this, then come ask me. It can be somewhat difficult, but as long as you feel good with this, then the next two are going to be far easier. Alright? Well done, guys. Hope you have a good one.